Okay, so I'm going to show us how to analyze problem set number 8. So I'm going to share my screen, and I'm going to share the desktop. And we're basically going to start with, you actually see me Googling some of our themes that we talked about earlier. But we're going to go do the same thing that I talk about every time, which is essentially having a clean, hygienic work environment. And I want to say, if you have any questions at all, feel free to chat or interject. Just make sure you unmute if you're going to interject. So for this for problem set 8, let's scroll down. We're going to preview, and let's get this going. I'm just going to download the RScript file, two things, the RScript file and then the RData file. And I believe you see it twice, by the way. You see it right around before question 16, and then you see it again right in part 3. They're identical. Just download it once. Even though you see an accompanying R code and a science RData file, they are identical. So let's download this, and then download the second one. And as I said before, you'll see it under part 3, and if you scroll up, you'll also see it right at the top. Now, if you've seen my sections before, this is what I like to do. I like to create a new folder, and we're going to just call this prob set 8. Remember that if you're going to set a path file or put a location for your script, don't use spaces. I would say it's bad because it's hard to tell if you have many spaces or one space. Let me go to the downloads folder. That's my bad. So you'll see a lot of us have downloaded here, but we see here our data file, and we see this here. I'm going to actually close RStudio. Okay. All right. So this is what you should see typically. So you go to your website, you go to your location, and then here you see basically your working environment. You'll see I added a few things to the script, and I'm also going to include a few corrections because some of the questions themselves were different. But if everything goes well, as it should be, if you have any problems, let me know. You should just be able to double-click, if you're using a Windows operating system, you double-click the scripts here, and here's your working environment. And I'm actually now going to stop this share, and I'm going to do a new share. I'm going to share just RStudio, because this is going to be our workplace. Because I'm going to mess around with this environment. One of the things I do want to show is, and I don't talk a lot about this. I hope at some point to have enough time to actually be able to describe each of these elements, but each one of these windows, you could say, the technical word is pane. But the point is, if you click on one of your panes, you should be able to click under the tab files. And this tells you as well what is in your working directory, your present working directory. So what I do, I just created a path. I created something on my desktop. You can put it under documents. You can put it elsewhere. And this is important because I added some extra script. But before we do that, let's just run the script here. So I just highlighted what I needed to run. You only need to install a package once, I should say, and you only need to load a package. You have to load a package every time you start a session. And you'll see the download window here. So it's taking a little while, but we're getting it. Okay. There is a little bit of a warning. I do want to say, I said this last week, our updates quite frequently. So sometimes you'll get a little warning about, I think the version we have now is 3.3.1 when we started the course. It's just not something to worry about, but it's just a small difference. So now we're going to define an object in our working space using the get working directory function. All this says is we're going to define a string or just a set of text, that which is our working directory. And because I have everything saved here, we're going to see that this is under the desktop. And if we go to environments, the global environment is here. You'll see this is actually under a different pane. You can customize, by the way a lot of the RStudio environment looks. If you go to global options, that's right. If you go to global options, you can customize the way everything looks. That's why if you look at my environment, it looks a little bit different. Also, if you're a big programmer and you hate staring at this white, you can actually get sort of a high contrast, different scripting console, for instance. Sorry, scripting file as opposed to the console. So here's the console in the lower left-hand corner. But pay attention to this environment. What we defined here is the working directory is just the string here. We use it using this function. And this will just print it. You could also just type this in the console, but let's run that. And this reminds us where we are. Now we're going to set the working directory just in case we're not sure. And I double-clicked it by accident, but we set it twice. And now we can do something different that is a little different than what we've done before, which is if we look at our environment, our global environment, we don't have our data frame loaded. Well, you can use the load function because we know for a fact, actually I'm going to add a bit of another function here, the directory function that I use quite often. And this just tells us what's in our directory. This will print in our console our directory. We can define that as an object too. But you can also look here. The point is, now that you know that your script and your data file are in the same location, you can use this nice, easy load function. And here we are. We have loaded our data frame, and check it out. We have 1,756 observations of 10 variables. We can do all the other kinds of things that we've done before. But let's move to this question about some of the analyses of the data set itself. So I'm going to do Control-L. That clears your console. It doesn't change your history, as I've shown before. If you want to see what I've done so far, you can see that. I just like to sometimes have a clean console. It's sort of like an Etch-a-Sketch that you shake. We're going to talk about a few functions before. But before we begin, I want to survey the functions. First, we're going to talk about the tally function, which is what we've done before. Then we're going to talk about the prop.test function, which is a proportional test function. And then we're going to talk about the t-test. We're going to revisit the t-test. And then we're going to talk about probability distributions and quantile distributions. The last two parts we've actually looked at before, but it's still relevant, I think, for us to examine. The main new function for us to pay attention to is this proportional test function. Well, what is it? Well, the best way to figure something out, if you look at my help tutorial, just go under tutorials for the class, I'll show you 4 different ways to find help. But here's the most old school way, question mark, and the name of the function. And if you see under help, under the help tab, you'll see that this is actually under a different package called the stats library. This is a base function. But Mosaic, being what it is, incorporates a lot of these other packages. They're so-called dependencies. What is the prop test? It's a test of equal or given proportions. That's what we're going to focus on. And you can do that for any of these other functions as well. Okay, any questions before going forward? All right, good. So what I want to focus on is if we talk about this data set, let's take a look at what this is, first of all. So names science. The names function will give us the names of the variables. I guess I have to do .r data and make sure the DATA, the D is capitalized. No, why is that not working? Maybe because I have it in, okay, there we are. See, so this is, it gets to the best of us. I'm not sure why I decided to put it in quotation marks. So names, science, Why was I wrong to put it in quotation marks? Because here's the object, science, actually. Science is the object. It's not a string. It's not in quotation marks. It's a data frame. It's a type of an object that is a data frame. Now we can also do other things. So here are the names of the variables. Here are the first few rows. We can do the view function for science. Basically, it's a interesting study asking people whether or not and we have a numeric variable, by their gender, their age, and their religion, whether or not each of these fields is scientific. Well, these are classic proportional tests, and we can tell that these are proportional by the way that the data are structured. They're either scientific or non-scientific. I don't think there's any missing value here. And because these are categorical variables, when we talk about proportional tests, we're dealing with categorical variables. I'm going to save this data file or this script file. If it's ever red and there's an asterisk, it means you changed something. And it's because I altered the code just a little bit, because I like to have some of these scripts in different lines. So here we use the tally function again. And we're always going to think about proportions when we think about proportional tests. We're not going to do percentages for now. And we're going to run the script. So what does this show? What is the proportion of people in the sample who think each of these fields is scientific? Well, there you have it. You'll see that people tend to think of accounting as not very scientific, right? 66% do not think it's scientific. Engineering, people think that's pretty scientific. It's an applied science. Of course, if you're in this hard sciences, a lot of hard scientists and physicists will say, well, engineering is not scientific. Economics is kind of interesting, right? It's right in the cross section there. Most think it's scientific. In fact, more scientific than accounting. And you can do that for each of these other variables. So this is a familiar function, right? You have the way it's expressed in Mosaic. They like to make their syntax modular. For the most part, they do have a few caveats. They like to use the formula function. So they have this tilde. They want to say the proportion is a formula that is this variable accounting. We're going to format as a proportion using the data science. That's it. So let's go through this question. The first thing we're going to look at is a one sample two-sided test for proportion. So I'm going to read you the question. A famous economist, we don't know whom. There are plenty of famous economists. They like to award Nobel Prizes every once in a while. They say that the proportion of the people in the population who view economics as scientific is equal to 0.52. So this would be the appropriate test is a one sample, two-sided test for proportion, with an alternative hypothesis that the proportion is not equal to 0.52. So in terms of the null hypothesis and the alternative hypothesis, I'm going to skip over that a little bit, but just think about this in terms of the null hypothesis is essentially the assumption that, how do I put it? That the assumption is that it is not, well, the alternative hypothesis is that it is equal to 0.52. The null is that it is not equal to, the alternative is that it is not equal to 0.52. So the null is that it is equal to 0.52. Or that we fail to reject that the true population proportion is not equal to 0.52. The main point here is when we do a one sample two-sided test, one of the things we try to do is we might have a guess about the population. We're going to test whether our sample is consistent with the population. Think about it as consistency. And this is where we use this syntax here. Here we have the function, and I'm just using a carriage return between each of these little elements of the function because these are the arguments. There's one argument you see here that isn't really explained anywhere, and I think it warrants a little explanation. Okay, but the point here, and I'll show you this. So you have the prop test argument, and what we're saying is, okay, we want to look at the proportion of those in economics who view economics as scientific. We're going to test the hypothesis that the true value is 0.52 using this sample, and then correct equals false is our final arguments. There is something called let's say yeah, okay, sorry, the name escaped me. There is something called a Yates continuity correction. So statistics, if you notice, has a history of kind of giving homage to the people who have produced knowledge before us. And this is one of those cases. So there's this guy named Yates. I've heard about this before. It's simply a correction that will actually increase your p-value. So if something is statistically significant, typically it will increase a little bit more. It's because what we're doing when we do a test of proportions, we're actually using a chi-square distribution. And if you set the Yates continuity correction to true, then in practice you're just going to end up with a result that's less likely to be statistically significant. In other words, you're more likely to have a type 2 error, but less likely to have a type 1 error. I looked this up when I was prepping for this section. It's not even really, it's rarely used, but you do have to assert this argument to be false, because if you use standard stats packages like SPSS or Stata, they won't do a Yates correction. It's just not part of the default. For the proportional test of equality, or for to test a particular value, you have to set that to false. So that's what that little argument is. You'll see that continuously. It's not a big deal, I'd have to say. So here, the main point here is we're testing whether or not the proportion is equal to this value. So what I'm going to do is I'm going to clear the console so we can focus right on the output here. And I'm going to click run. We're going to run this element of the script. And what do you see here? So you notice that the first line of the output in the console, it describes what it is not doing. It is not doing the Yates continuity correction. Here's the chi-squared statistic with 1 degree of freedom, and there's the p-value. Notice the p-value is around 0.08. So the true p is not equal to 0.2. So the null hypothesis is that 0.52 is within that spectrum. And if we look at the confidence interval, we see that we fail to reject. We do in fact. What do I say? If the true value is not equal to 0.52 and it is not significant, then we fail to reject the alternative hypothesis, and we can accept the null that the true value of 0.52 does lie within our range of plausible estimates. And how do we know that as well? Well, we see that quite intuitively through the 95% confidence interval. That means in a hypothetical universe of 90, if this were to be continued 95% of the time, that this would we would see a value within this range. So the p-value here is worth focusing on. I want to do something I'm just going to show you what happens when you do the Yates correction, and pay attention to this p-value right here. So you'll see that the output is identical. As you'll see this is with continuity correction. I don't know if you see the window. It looks like my battery's a little bit low, so I'm just going to plug it in. Are there any questions as I've proceeded? We're going to go through iterations of this argument, and you'll see that the syntax is pretty modular, which I appreciate. Okay. 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 Everyone's still there? Good. Okay. Okay. So the next question refers, so I just want to show you, so the p-value is slightly inflated here. And again, when as I said, you can just go to Wikipedia. I looked this up, the Yates correction in Wikipedia. It's one of those things that there's so many different statistical tests and permutations. You know, it's just one of those little permutations. So the next question is, so we're going to set this back to false. The next question is, using your results from the previous question, what is your conclusion at the alpha 0.10 level? Well, 0.10, we see that the p-value is actually less than 0.10, even with the Yates correction. So we can basically say that at least at the 10% level, we can reject the null hypothesis and accept the alternative hypothesis that the true proportion is not equal to 0.52. Now,
can I jump in with a question?
Yes, please.
Okay, so on this one, on the prop test, what is your conclusion based on the alpha level of 0.0?
0.1.
We didn't set 0.05.
What was that?
We didn't set 0.05 as the alpha.
No. You set well. So to be clear, when you typically do the test initially, the traditional view is to set an alpha of 0.05. The follow-up question asks what happens if you were to accept an alpha of 0.1. Typically, you want to, by convention, we focus on an alpha of 0.05. That's what defines what is statistically significant or not.
Right. I mean, that's the 95%, but that's what I'm trying to understand is how do you change the alpha from 0.05 to 0.1? Or you're about to see it when you scroll down. There it is.
Okay. That's a great question. Yes, it's exactly what I was going to show you when I scroll down. So you see this in the last bit of the arguments. And this is why I like to actually use the carriage return when I type this out, because you'll see that every argument is identical except for this one little part, which is this confidence interval. So the default confidence interval, surprise, surprise, is to use the 95% confidence interval. And if you look at the argument here, you'll see this under the help file. Confidence level of the return confidence interval must be a single number between 0 and 1, only used when testing the null that a single proportion equals a given value, or that two proportions are equal. Ignored otherwise.
So obviously the default is 0.05.
That's right, and that's canonical. That's just what, that's what people are in search of when they're looking at these sorts of things. People are going to be more skeptical if you have a confidence interval at the 10% level. Does that answer your question, Shep?
Yes, thank you.
Yeah, my pleasure. So if you look at this here, the point I want to show is because we're using the same test, Shep, is the p-value is identical. Same with the chi-squared statistic. So our analysis of the data and our conclusion is identical. The only thing that we're doing is we're slightly narrowing that confidence interval. So rather than have a confidence interval that's slightly wider, we have one that's a little bit narrower. In fact, if we wanted to do, and then I think if we do it at the 0.01 level, do you think that confidence interval is going to be wider or more narrow?
It's going to be wider. It'll be 99% of the data.
Exactly.
Okay, so I have a question on this, and I think it's the phrasing, because I think I haven't said it out yet. When I say it out loud, I'll probably start tripping on it too. Let's leave it at 0.01, and let's look at this data set. So the null hypothesis is that 52% or 52 proportion don't believe in whatever. I forgot what we're working on. Actually, so at 99, it's outside of the confidence interval. Wait, that's a 0.1% confidence interval.
Yeah.
All right, now I'm confused.
No,
at 0.05, I thought 52 was within the confidence interval.
Yeah. So
what I'm tripping up on is we didn't reject the null hypothesis is what I was going to say. Here we do because 0.52 is outside of 0.54.
Okay, so yeah. I wanted to say, so the answer to answer your question, when you have an answer at the 10% level, your interval is going to be just a little bit notice that the interval here is going to be a little bit wider than the interval at the 1% level.
Right, but in this case, we reject the null.
Exactly, because you have if you have a confidence interval at the 1% level, you're actually having a more severe test of significance.
Right. Put it back at 0.05 for a second. Maybe I wasn't reading it right.
Okay, absolutely. So here, we'll do this action sequence.
Because for 0.05, I don't think we didn't reject the null.
That's right. We failed to reject the null.
That's what I needed to hear.
Right. So here's 0.05. Is that right?
That's not the same number we got.
It is not the same number. Let me see what happened. Okay. So here's the 95% confidence interval. And that is with an alpha, that should be with an alpha of 0.05.
So the correct way to describe that would be we failed to reject the null because 0.52 is between the 95%. It's inside the distribution curve.
Exactly, but it's right at the lower bound, right?
Okay.
So it's not ginormous. It's not that impressive.
All right. I just wanted to make sure I had the words right.
Yeah, no, totally fine. And then if we look at the 10% level, now a confidence level of 0.10, you'll see that the range of 0.5, 0.539, 0.540 to 0.543 is more narrow than where were we? You know what I'm going to do? I'm going to show you guys something that is what I like to use sometimes, and this is an option that we can do that will help us read the output a little bit more cogently. And this is just to set the number of significant digits to 3. I wouldn't recommend it, especially for the problem sets, but sometimes it's good if you just want to get an easier read of the data. So here we are with a 95% confidence interval. Here's our test, our default test. See how that's much easier to read. And then we're going to set it with the 10% level. By the way, the options function, I want to do a tutorial on just on that. So here we have it with 0.5, 0.540 and 0.542, as opposed to where was it? Where are we? Yeah, 0.18 to 0.65. So at the 95% level, we have a wider confidence interval than we do at the 10% level. And then at the 0.01 level, I'm not sure if that's the right syntax. Let me make sure I'm doing that correctly. Okay, yeah, I think that's correct. But the point here is that the p-value is the same, and at the 0.1% level, which is a more severe statistic, you're going to reject the null. So the point is, at the 10% level, it's a more severe test. So another test we're going to look at is whether or not, right, I wanted to correct this, which is, in addition to testing confidence intervals, we also want to see whether or not a value is greater or less than a particular value. And this is a one-sided test. Now I want to emphasize this because a two-sided test answers the question, is the value what it is we think it is? In other words, is the true population value, P, equal to 0.52? Here we're asking something a little more modest, which is it greater or less than that level? And here the hypothesis is that the proportion is greater than alpha equals 0.33. The point I want to emphasize here is actually this new command, which is identical to everything else, which is alternative equals greater. If you wanted to test that the true proportion is less, then you just type in, I believe it's just less. Let's just see if that's correct. Yeah. I'm going to change the options command, the digits to 7 again, and I'm going to clear the console. So if you want to test, if you believe that the proportion of accounting is less or is greater than 0.33, and you want to test that, then you just use this function, and you find that the p-value is 0.13, which is at the greater than the 5% level. So, well, you know, it's funny because, oh, right. Based on previous research, you have little reason to believe that this proportion is less than 0.33 in the population. Well, what do we find here in the data? Well, we find that we fail to reject the alternative hypothesis, so we do in fact conclude that the value, the true population value of the proportion of people who view accounting as scientific is greater than 0.33. Now this is where I take you back to the data, away from inferential statistics. If we look at the actual data, you can actually see what the data say. Well, our sample says it's those who say it's scientific is 0.34, those who say it's non-scientific is 0.66, right? So if you're going to test, let's see, right, if you're going to test the hypothesis that it is greater than 0.33, then we have good reason to believe that that's the case based on our sample alone. I'm sorry, no, we don't, right? Because our null hypothesis is, our data are consistent with 0.33. I'm sorry, this was a misreading on my part. I rounded incorrectly. So we actually find that the data are consistent with a proportion of 0.33. So we fail to reject the null hypothesis. So another test to examine is to look at whether or not the proportion that we find in the sample is less than an alternative. So I want to make sure that the question was worded correctly here. I think one of them in the problem set was a little bit different than the syntax when people had talked about it on the discussion board. If you look at yeah, okay, so the alternative hypothesis is that the proportion is less than 0.85, and the null is that we fail to make that claim. So here all we do is we set this proportion, this extra argument here, to less. And what do we find? Well, we find that the alternative hypothesis, we can safely conclude that the true population proportion is less than 0.85, given our data. And we see that our p-value is significant. We do, in fact, reject the null, that it is not. And remember, this is a one-sided test. So whenever we do all the alternative arguments, all we're doing is we're just saying greater or less than. And if you read the description here, notice that it's only used for testing the null that a single proportion equals a value or that two proportions equal, otherwise it is ignored. And we're going to look at that, I believe, in the next section. We're going to tally our results here. Let's say we're interested in probabilities by views by gender. So here we're using this pipe function. So we're saying conditional on being male or female. What is your view on economics being scientific or non-scientific? And that's a fairly simple question. Now I want us to move to this two-sided test, because I think, first of all, it's far more common. And typically, you'll see this more in experimental data. You want to see whether or not two groups differ. But before we do that, are there any questions about the one-sided tests that we looked at before? All right. Yeah, Shep?
No, I'm good. Thank you.
Okay. I think that the confidence intervals get a little bit confusing when you try to specify the null and alternative. The main point is you're still using the proportional test argument. It's just you're gonna specify in this argument here what you want to set as your sort of your a priori proportion, what your belief is, and then you're going to set your alternative to less or greater than, or you're going to, as we saw in the first example, we're going to specify also the confidence level.
Yeah, from the lecture, the P would be what you were calling the P hat.
Oh yes, absolutely, yeah. Well, yes, because let me think about this, Shep. Yeah. Yes.
Yeah.
Exactly. This
Can you explain that? It confuses me too.
So the P here in the syntax refers to the P hat in the data. That's almost always the case. When you ask about what the point estimate is, you're looking at P hat. Patrick, did you have a question?
Okay, so the P hat is the point estimate?
Yes, exactly. Whenever you're looking at, so typically we use Greek symbols, as you might recall. We use Greek symbols for population parameters. For our sample parameters, we'll use Latin, except with proportions. And this is where it gets a little confusing, because we're talking about p-values. So p hat refers to the sample, p refers to the population. But in our syntax, all we're saying here is p is equal to the proportion that we believe to be true in our population, but we're testing it in our data because that's all that we have. We never observe the actual true population parameter. We only test whether or not it's plausible. Does that make sense? Patrick?
Yeah, I think so.
Okay, all right. So we covered one-sided tests, greater than, less than. We talked about this, this correction, Yates correction, and we talked about confidence intervals. Now I just want to show you, if you look at what's more common, these conditional arguments. Here we see some differences in proportions that might be interesting. You might want to know, if you look at this, for instance, if you look at economics, I want to show you, highlight this first sort of crosstab. It's called a cross tabulation. In shorthand, we'll refer to these as crosstabs. You might want to see whether or not this difference is statistically significant, right? So and this is when you do a two-sided test of the hypothesis that there's no difference. So here the null is that men and women are identical, that what you see here in the data, this difference of 57 versus 43 and 51 versus 49% for men in viewing economics is not statistically significant. It's just a function of noise. Well, this is probably what you're going to do in about 90% of your proportional tests. More often than not, you're going to want to know if the differences, the patterns you observe in your data are statistically significant. And here you'll see the argument is the same as before, except we have this groups argument. So instead of the P equals something, we have groups equal something. So this defines our groups. Comparable to our tally function, this is our conditioning variable. So we're saying, what is a proportion of those who believe economics is scientific by gender using the data science, removing the Yates correction. And this will automatically produce us the p-value that, if statistically significant, will tell us at the 5% level, or the alpha point equals 0.05 level, whether or not there's a difference in between men and women in the way that they view economics as scientific. What do we find? Well, we actually find a p-value that's pretty low. So we have a chi-squared statistic that's high, and we have a concomitant low p-value. And here's the confidence interval that we find for our point estimates. What is our point estimate? Well, remember, it's the difference in those proportions. If you go through the quizzes, that's what our 95% confidence interval tells us here. It tells us the range, how large can we expect within the 95% confidence interval to be the difference between men and women in the proportion that they view as economics as scientific. Right? So.
Okay, so what is proportion 1 then?
Proportion 1 is the first value within the sample. And proportion 2 is...
That's actually, it's backwards. So wait a minute.
Well, no, it's the first one. So let's do the cross tabulation of this right here. So proportion 1 is identical to females. Proportion 2 is identical to males. And this is due to the ordering of the gender grouping variable. So if you had groups that if you had a data set where it was male-female reverse coded, this factor variable were reverse coded, then you would have a different point estimate. The absolute value difference would be the same though, and that's the relevant point.
Okay.
Right, okay.
So this would only be useful if we changed it, I mean, as opposed to doing like the tally, the only way it would be useful was to change it from, let's say, 5% to 10% to see something different.
Well, you wouldn't see anything different, Shep, because the absolute value of the difference between men and women is the same. So whether or not we're swapping categories for male and female, the proportions are identical.
Okay, I guess I was trying to figure out is what's the point of doing this over just doing a tally with proportion?
Well, because the tally does not tell us whether or not the difference is due to random variation or whether or not it is statistically significant at the alpha 0.05 level. And this tells us that the difference is indeed statistically significant.
Okay.
And it also gives us a confidence interval that tells us our range of plausible estimates. So our difference between men and women who view economics as scientific could be quite large. It could be that women on average view economics as more scientific than men do by a margin of 10%. But it could also be quite small. It could just be it could be 1%.
Okay.
So it gives us a range of plausible estimates. It gives us a level of statistical significance to evaluate whether or not the actual data themselves, the descriptive data, whether or not we can actually infer whether or not there's any difference between the two. And so here we can conclude at the alpha 0.05 level that in fact there is a statistically significant difference, and you can also publish with this, I'd have to say, Shep, right? So the point in science is, you know, the 0.05 alpha level is king. If you want to publish something, you will often want to publish something that is statistically significant. If you have a huge difference, but it is a very imprecise estimate, then it's not very interesting. Conversely, however, if you have a statistically significant difference, but it's not very large, that's perhaps not interesting. So that's also another important point to make. So I just want to make sure that this actually asks the same question. I know there was a typo here somewhere. It asks the same thing. So here actually the question, you know, we do in the syntax ask you what the point estimate is. Recall that the point estimate is just the difference between the two groups. And here again, you find a p-value that's very small. This is scientific notation for those of you who aren't familiar with it. So this is actually equal to, you just move the decimal place over 5 points. So it's basically 0. In other words, what we find is that proportion 1 as opposed to proportion 2. Proportion 1 is less than proportion 2. And remember that proportion 1 is female and proportion 2 is male. So that's always something to keep track of, actually. I mean, the fact that categorical variables, the grouping variables, are arbitrarily ordered can be a little bit frustrating if you only look at the output. This is why it's always important to use the function and actually look at your data first before you do inferential statistics. So this was just a test that looked at engineering as the outcome. And here we find that that difference is statistically significant. And we know that this category is female and male. And by what magnitude is the 95% confidence interval? Well, it's pretty close to a 0 difference between the two groups. But that's unlikely. It's far more likely that we're going to see a difference of closer to our point estimate, which is, I don't know, what is it, about 7%, a 7% difference.
Nate, I was wondering, how do we have negative confidence intervals?
That's a great question. So the negative confidence interval is a result of our hypothesis test, which is the fact, it goes back to what I was saying before, which is that our order of our point estimates refers to whether or not we believe the difference is positive or negative. In the previous example, with economics, we have a tally where the proportion of women who view economics as scientific is greater than the proportion of men who view economics as scientific. That means that our difference is going to be positive. That means our difference is going to be positive. Our 95% confidence interval estimating the size of that difference, which is about 6%, is going to be positive. So a large number minus a large number is going to be, a larger number minus a smaller number is going to be positive. What we have here under engineering, if we're going to tally the engineering, here I'm just pressing the up arrow, by the way, if you want to go through your history.
So is it just how you frame the question?
Absolutely.
Okay.
Absolutely. It's about framing the question. It's about what hypothesis are you testing? Are you testing the hypothesis that women are one proportion is greater than the other, or that one is less than the other? And the confidence interval, think of these as plausible values of that difference. So if we just do I'm going to just show the tally function again. If we take this value and minus this value, we're going to have a negative value, right? So this is a female-male engineering diff. I'm just typing this out as an object. This will be a negative number. And we're going to print this, female engineering diff. That's a negative value. So what we know is that our negative value is about that females are 7% less likely than men to view engineering as scientific. Well, our 95% confidence interval is an estimate of that range of plausible values within conventional statistical standards. So, and that's what we see here. We see that when we have, wait, did I do that right? Did I do engineering or? Oh yeah, here's our confidence interval. So check this out. So here's our confidence interval. I'm going to reprint. So that's, well, female So what we see here, Patrick, is this is our point estimate of the difference, which is negative. Here's our 95% confidence interval, which tells us that our range of plausible values at an alpha of 0.05 is anywhere from 10% less to really 4% less. And whatever that difference is, we know that that's highly statistically significant. So you can at least say there is a difference. We're not exactly sure what it is, but we know, given our p-value, that it's very low.
Yeah, for what it's worth, in the lecture, it's steps 4A and 4B for figuring out the two-sided. You actually have us convert the z to absolute.
Yes. Well, certainly. That's different than the output here. So that's
but it's the same number. Well, so in this case, it's prop 1 and prop 2, but I think it's the same idea. Because the range for step 4B, which is p-value, is 2 times p, 2 times p times z greater than absolute z.
You're saying you estimate the standard error times 1.96.
Yeah, way past that.
What's
that?
We're
trying to figure out. It's past that. It's where we're trying to get the actual. We're doing the comparison before we do the conclusion. In the steps, you actually tell us to use the absolute value of everything. So.
Oh yeah. I'm just helping you read the output here, in the sense that if you look at the confidence interval here and you read the outputs.
Right.
I was just trying to answer Patrick's question.
No, I understand. It's just that when we did it, I mean, the same thing would happen on a two-sided, but I guess my point is when we went through the steps on this in the lecture, we converted all of those to absolute because it's the same ones.
Yes, exactly, which is why typically when you see this in scientific reporting, you'll typically see this line highlighted here. You'll typically see...
They'll leave it negative?
What's that?
Will they normally leave it negative if it is negative?
They won't, well, this is the way I've seen most, like at least in the social sciences. If you're going to report a difference, you will, again, it depends on framing. I think most people are not concerned with whether or not the difference is negative or positive, because that's an arbitrary function of whether or not you put male or female first.
Right, understood. I was just curious, since we went through the trouble the formula that we used for the lecture was absolute. That's why I was asking. Yeah, well,
I think that's more important, right? Because what we're looking at is our difference from 0. The fact is that our lowest estimate is still 4%. A 4% difference is more important, far more than the sign. But I just wanted to emphasize that you shouldn't get hung up on the fact that this is sometimes positive and this is sometimes negative.
Okay.
So there is a difference between the way you'd write up and interpret material and the way that the output is sometimes given. And yes, I would say if you want to emphasize the difference and write it up, if you want to write up the 95% confidence interval, write it up as an absolute difference. Now, why is that, Shep? Do you know why we would write the absolute value of the difference of the 95% confidence interval, why that would be more interesting?
No, I don't actually.
Well, because our H naught, our null, is that the difference is 0. And then the H alternative is not equal to 0. So the point is, whether or not we put positive or negative signs to our 95% confidence interval, we know without a doubt that it is not equal to 0. So here our p-value permits us to reject the 0 difference and accept the alternative hypothesis.
Okay.
So does that answer your question more or less? Is that helpful, Shep?
Yeah, no, I'm good. Hopefully
okay, all right.
Patrick's too, because I kind of intervened at the end.
No, that's good. That's good. I like these types of questions. We're going to go back to t-tests, actually. And this is basically to show that when we talk about tests of proportions, sometimes we're also talking about mean differences by proportions. So I'm just going to comment out this so you can actually read it within the syntax. So the question here is whether or not age differs among people who view sociology as scientific or not. And here you simply use a t-test. And the difference here is you're looking at age and you're using the formula equation. So you want to know by category of attitude towards sociology, given the mean of age, does that differ between the two groups? And what we find is that, yes, in fact, there is a difference in the means between those who view sociology as scientific and those who do not. And the point estimate here is for those who view sociology as scientific, they tend to be younger. They're around 48, 45, as opposed to not scientific, they're around age 49. So the innovation here is when you do a test of proportions, sometimes you're asking a slightly different question, which is you want to know whether or not there's a difference in a continuous variable or numeric variable by levels of a categorical variable. And you can do that here as well when you see that age does not seem to be a factor in terms of whether or not you view economics as scientific. And here's the difference. And the point estimate here would be the difference between the two means of these two groups. Let's see, we're almost out of time. We've been a little bit over. I just want to highlight the fact that, let me see, we've already covered some of these other things. I think the rest of these are relatively self-explanatory. We covered the probability distributions before. Somebody asked in lecture, we covered this in last section, so if you want to look at this in greater detail, just realize that with the p-dist function, you're actually taking a distribution and you're deriving from a critical value. What is the p-value? So I want to show this to you actually in our example. So I'm going to just give you one example of each. So, and as I mentioned before, we used to do these with tables back in the day. I think when I was an undergraduate, they just forced me to. Let's do a proportional test here by engineering. And what you see in the output is you'll see a chi-square statistic. You'll see an associated p-value. I'm just going to play around, actually. I'm not even sure if we'll get the p-value here, but let's just see if we put in this critical value here, what p-value we get. Well, actually, that's a little misleading because you actually use a slightly different distribution than the t-distribution. The t-distribution is for the t-test. The point here is, I would say look at lectures, since we're running out of time, look at lectures from last week. I actually get into these quite into detail. But the point is, if you want to know the p-value given a sample size and a critical value, you'll come up with a p-value here. And you'll have a nice graph here, actually, which I like quite a bit. If you want to look at for a critical value for the t-distribution, you'll see that this is the case here. Someone had asked earlier, I think, and if you look at the discussion board, they had asked, why do we use a critical value of 1.96 rather than 1.6245? And the point I was trying to make in my comment was the fact that I don't think maybe it was for the t-distribution, but for the normal distribution at least, if you have a critical value of well, where are we now? I don't want to do the t-distribution. I want to do a normal distribution of 1.96. Then you'll see that the actual distribution is half of 5%. So if you want to do a two-tailed test in a normal distribution, then you have that distribution defined by two critical values, negative 1.96, as the lecture explains, and positive 1.96. And you'll see that in this graph, you'll see that the tails of the distribution, the green and this blue here, add up to 5%. So whenever you use a normal distribution, you're going to have the critical values at 1.96. But if you look at, I think, around slide 56 in today's lecture, someone had asked, why do we use this value here instead? And it's because using a normal distribution, this is the way that you define the 5% level, the alpha of 0.05 for a one-tailed test. If my memory serves me correctly. Okay, I'm a little bit off. Let's see if that's right. Okay. So, well, anyway, you'll
1.645.
1.645.
45.
Okay, thank you. Yeah, I'm going off my memory here. I thought there was a 2 there. Thank you so much. Okay, and so that would be a test of a value greater than of a right tail test, and then the negative critical value, of course, would be the inverse of that. It would be the other side. Thank you. I don't know why I put a 2 there. I think I got to rewrite my response. I think I put a 2 there. That was just bad muscle memory. Anyway, you still have to just go to look at my section last week, and you'll see that the point is, for every critical value, there's an associated p-value. There are 3 things that are interrelated: distributions, actually 4: sample sizes, distributions, critical values, and then finally p-values. We can interrelate those and examine one given the other using these kinds of distribution functions. That used to be a lot of hard work. I want to take us back to this confidence interval function by itself. We talk a little bit about nesting functions. I've done this before. When you do a test, we're going to do, say, the test of those who view biology as significant, or as scientific, rather. We can do this right here. You can also use this confidence interval function. Whoa. Okay, so yeah, that's you don't want to go in there, but that's actually the actual function that you have for that. For any test, you can actually give the lower and upper bounds of that 95% confidence interval here as well. So the point is, you can do a proportional test, and rather than specify the alternative, you can actually do a confidence interval as a function. And here is you know what I think I was doing incorrectly, guys, actually. And this was a problem with the syntax, I believe. When you use the confidence, at least when you use the confidence level here, you're defining the confidence interval. So an 80% confidence interval means you have you have a, what would you say, a narrower set of values than if you had a 99% confidence interval. You're more likely to you have a lower p-value or a statistically significant p-value with an 80% confidence interval than with a 99% confidence interval. A 99% confidence interval, it's going to be a little bit wider. But the main point I just want to emphasize is this function called confint. You can actually apply it to other kinds of arguments. And again, it's in the, this is important. It's in the stats package here. But basically, for lots of different things, I think people have done it for linear regression models, whatever else you're looking at. So today we covered, I think the main focus we wanted to emphasize was this prop test function in conjunction with reusing the tally function. So with a proportional test, you have, you almost always set the Yates correction to false, You can either define it as a two-tailed test by groups, or you can do it as a test that is either equal to a particular value, where in which case you would not have this alternative argument here. So if you want to just do the test about as to whether the proportion here is equal, you would see that you would have the same p-value. But if you want to test a one-sided test, whether the alternative is less or greater, then you do less or greater. So those are, at the core, basically three tests. Two-sided test by groups, a greater than test, a less than test. And the main function is the prop test function. All right, thanks a lot, everyone. And feel free to interject or email with further questions as well. And keep in mind, on Wednesdays, we're still doing the, I'm going to focus more on data management as well, which might be useful for your final project. And that's it. Thank you very much, guys.